Good afternoon, everyone. I welcome you to the webinar on natural ventilation for your building today. I am Yashima Jain and I'll be moderating today's session. This is the fifth technical session of the 10-part series, and we hope that you have got the chance to review the self-learning module on today's topic. Next slide, please. Now, before we begin, I would like to acknowledge the support of our sponsors and affiliates. Next. Here are a few announcements before we actually begin the session today. First, we, the organizers of Solar Decathlon India, would like to congratulate the teams for submitting their first deliverable. You have gone past the first milestone in your journey. We are excited to see the reports and will give you feedback and comments by October 28th. Now, next, there will be 2 software-related sessions in the upcoming weeks. A session on Climate Studio would be conducted on Saturday, which is the October 24th, and on Design Builder would be conducted on Sunday, which is November 1. Now, we will share the details about these webinars with you soon. And lastly, all team members need to complete their online learning modules by December 31. Without this, your team will not be able to qualify for the finals. And we have noticed that some of you are trying to log in to the learning platform with your email IDs as usernames. But this won't work because your usernames are not your email IDs. Your user IDs were emailed to you, and we request you to please copy and paste those into the interface to log in. Team leaders, please make sure that your team members are up to speed with the online learning modules. Next slide, please. Now, today's session is being conducted by Swati Puchalapalli. She has more than 20 plus years of experience in sustainable design, computational analysis, and environmental policy work. She is a strong proponent of passive design and combines learnings from vernacular buildings with a simulation-based, data-driven approach to building design. She focuses on high performance and high comfort, leading to net zero design, along with value of engineering in the areas of energy, water, and waste. Her projects range from sustainability consultancy to policy research and training spread across various continents. She's also a founding member of the GRIHA Council and a visiting faculty at CEPT and Manipal University. Swati is also a member of the group of advisors for Solar Decathlon India. Now today, she will present the best practices on implementing natural ventilation for comfortable net zero buildings. Now this is your opportunity to learn about this topic from one of the foremost practitioners in the field. As always, you are free to send in your questions at any time during the session. We will take as many questions as time allows during the session and provide answers to unanswered questions in a write-up afterwards. And with that, it's over to you, ma'am.
Thank you very much, Yashima. Thank you for inviting me to share my thoughts on the subject. So welcome everyone. Good evening. I hope, as Yashima said, that you've been through the self-learning modules and you have gone through, because a lot of what I'm going to present, you'd be able to follow really, really well if you had been through the self-learning modules already. So let me start off. As Yashima said, been working in the area of natural ventilation for several years, and I would like to sort of present some of my thoughts and ideas and the way that we approach design in this particular field. So just before I start, I'd like to sort of run through a very successful case study of natural ventilation. This was done many years ago by architect Shankar Narayan. It's based out of Hyderabad. It's a school for Islamic studies. It's called the Henry Martin Institute in Hyderabad. The thing about this, I visited this a few times in peak summer in around April in Hyderabad at around 2 o'clock in the afternoon, where when it was really around 40 to 45 degrees, around 42 degrees outside. It was a very hot summer day. And what was really very interesting to notice is that every single person in this office and in the hostels that were next to it, these are the hostels and this is the office that you see. All of them were working in a natural with only the fans on. There were air conditioners in all spaces, but no one used those air conditioners. The building was performing perfectly in spite of the harsh external climate conditions. And and they told us that this is how they have worked throughout the year, and they've never had to turn on an air conditioner in several years from the time they occupied the building. This was in 2010, and they had occupied it sometime in 2005. Also, they also mentioned, this is they had also used they also tried to integrate PDEC or passive downdraft evaporative cooling system. But what was interesting is they said that that wasn't really working well, and they wish that they had used more simulation to get the design right out there. They had a lot of features that you would usually notice, lot of design principles on natural ventilation that were integrated here, and they were integrated in such a way that the design works, and the design works very effectively. And what you see on the right side are secure ventilators. So most often we think about natural ventilation only during occupied times. They also made sure that it was working at night when everything was closed down and the building was able to cool down at night. So this is a little bit about Henry Martin Institute. Works extremely well. It was the most interesting aspect of this building is that it was designed around the same time as another very famous, well-known green building in the same location as Hyderabad around the same time. While that costed 5,000 rupees a square foot to build, this costed 500 rupees a square foot. And this worked completely on natural ventilation, whereas that did not as much. Another thing that had a lot of imported materials, whatever, and this was completely built with local materials and local artisans. So there you go. So there is an extremely good example of natural ventilation where it really works. And if you get a chance, if you're in Hyderabad, I would recommend that you go and visit this place. Another one that I'd like to show is again another case study, but this time it's a rather unsuccessful case study of natural ventilation. It was designed to be a naturally ventilated building, and we were brought on board about 4 years after it was built, saying that the children, because as a school, were having a lot of heat stress. They found it extremely uncomfortable during summers when the school was operational. It was and they were not able, it was also exam time, so they were not able to work effectively or study effectively. So we went around looking at what was going wrong in this building. As you can see, the windows seem to be adequately shaded. It seems to be a nice high thermal mass building, seems to have the right kind of jalis and shading devices. So what went wrong and why was it not working? So when we went and started analyzing it in detail, we started again, this was in Hyderabad again. It was a large 140-acre site, and when we start looking at it, we started from the outside. So what we noticed on the outside is this, that when you take a thermal image of the heat of a surface, these were spaces right outside the classrooms. During when this was sometime in May, as you can see. And when we took radiation images of the surfaces of the various surfaces across the campus, when there was direct sun on these hard pavers, on these external paving, you could see that the surface temperatures were close to 20 degrees higher. Okay, but that was expected. very much expected. But what was interesting was that even after sunset, after the sun had sort of moved away and it was no longer under direct sun, the temperatures were still hovering around, 20 degrees higher. External temperatures were 31 around this time. Whereas the surface temperatures were still around 48-50 degrees in some of these courtyards which were exposed through the day. So this was noticed across the Ham campus. So which basically meant that it was, as you can see on the right, it was a completely hard paved campus. There was not much shading on the hard paved areas around. These were all green areas, but these were all hard paved areas, and they were hard paved with quite dark materials. And these were, I think, they're hard paved with brick actually, and these were picking up heat during the day, and at night, they were releasing the heat, and of course that increased the overall temperature in the site even after sunset. So what this meant for the buildings is that at night is when the buildings tend to cool down. In a harsh climate like Hyderabad, the nighttime temperatures are lower and the building usually tends to cool down at night because the temperatures outside are cooler. But however, because the external temperatures were not cooling down as much, as you would like them to, the ability for the buildings themselves to cool down or to release heat that was stored during the day was reduced. So that added to the discomfort. Then we went down to looking at the exact, where is this discomfort happening and why is it happening? Let us look at these spaces in a lot more detail and start going into the inside of the spaces. So this is what we were looking at, a set of classrooms. There are two sets of classrooms. One was this set of classrooms for senior block. They were oriented northwest and southeast. They were oriented for catching the prevailing winds, which was perfect, which was really good. For both the southeast and northwest winds. This is these are monsoon winds, and these are the sort of summer winds. They were oriented right for wind. However, they were oriented towards the northwest, which had a lot of direct sun. So they were not, there was more importance given to the wind orientation than sun. However, that could have been countered in the form of some kind of external shading. But that was not there. So let us go into the classrooms itself. So here is a typical cross section of a classroom. There's a class. There is shading on the northwest side. There is quite a deep overhang there, and on the southeast side there is a corridor. On the northwest side, the windows were broken up like this, that you can see in the images here as well. The bottom was a metal panel. The top was actually a fritted panel. And the window itself was broken into a fixed pane and louvered section for natural ventilation. From an outset, you know that, yeah, it looks fine. I mean, why not? That seems all right. Seems to be enough ventilation. There seems to be enough opening for the airflow to happen, because these were there on either side of the room. So these kind of windows were present on both the northwest and the southeast sides. However, when we went and took some, again, the same infrared images and surface temperature images of this classroom, this is what we noticed. We noticed that, the top, number one, was fixed pane. And it was actually as warm as, as the metal frame, even though that was glass. And that was because of the pinhead. It was a pinhead security glass with metal wires embedded in them. So that was leading to that kind of a heat ingress and from that section. This was the actual glass section, and as you can notice, the glass itself was not too bad. But the bottom section, which was the metal section, the metal spandrel panel, was going up to 55 degrees, especially when the sun hit the panel. Even when the sun didn't hit the panel, it was still at least about 10 to 15 degrees warmer than the walls around it. So that was what we noticed. And another thing that we also noticed is that the frame was quite, was much warmer. The louvers also were warmer. and the blinds were drawn. Why were the blinds drawn even though there was shading? Then it was because, you know, there was not adequate shading and the blinds were drawn, and this cut out any kind of natural ventilation that was possible. The natural ventilation openings were blocked because of the blinds, and that was because of the visual comfort issues that they were facing. Again, a similar kind of issue was also noticed towards the corridor. This was a completely shaded section, but even in the completely shaded section, you could see that the metal panels were a lot more warmer than the walls around it. So when we started going down to details and identifying various issues, this is what we noticed. The top fitted panel was fixed, and there was no way there was a stratification layer. Another thing that I is the temperature and humidity. When the external humidity was at 29 degrees, the internal was going up to 36%, 29% internal was going up to 36%, and even more actually. It was going up to 40-45% as well. Internal temperatures were okay, but humidity was quite high. Temperatures were around 35, whereas external was 36. So what that meant basically was the ambient temperature seemed all right. However, there was a perceived increase, or the felt temperature was much higher than what the ambient temperature was. Added to that, the humidity levels were going higher, and that led to a certain amount of discomfort. So here you go. The fritted panel on the top was fixed. It was also pinhead glass, security glass, so it was working as a radiator, increasing the radiant temperature in the space. The louvered openings were open, however, because of not sufficient shading, the blinds were drawn and they were blocked. The louvered openings were also metal, so which were also picking up heat. So the incoming breezes picked up the heat from the louvers as they entered the classrooms. The lower metal panel was acting as a radiator, especially when the sun hit it. And there was the stratification layer, and there was, you know, the warm air rises up, and there was no way for the warm air to escape. So when the ceiling fans were turned on, the discomfort in the classrooms went higher. So what was the solution? There were several things that were done. First things was to change the type of windows. So change it from a clear glass, remove the pinhead glass and put in glass louvers. Sliding windows instead of these kind of windows, and an insulated panel was integrated. External shading was integrated. So when we did all this, what we noticed, and we went back and took measurements in various classrooms, and we did the mock-ups were done in just 2 classrooms, and the rest of the classrooms were available to take as a baseline condition. So again, the following May, when we did the same when we went and measured, what was interesting to see is that the window modification, where we did window modification and external shading, the temperatures dropped by 2 to 4 degrees, depending on the outdoor temperature conditions. And this sort of brought it down into the comfort range through most of the day. So you can see why, you know, that was the reason why I'm showing this is to show that, you know, you can learn a lot from something that doesn't work. You can learn a lot more in trying to analyze what didn't work, and learning from from what went wrong there. And retrofitting this and getting these kind of measurements helped us understand a lot about all the various things that impact natural ventilation in any design. So the difference, as you can see, between the two cases is this. You know, the biggest issue with any natural ventilation design or high performance design is a high performance design doesn't always result in high performance operation. And why doesn't that happen, and how can you make that happen? Especially in a naturally ventilated space, the crux of the issue is ensuring that you design with comfort as your primary objective. Okay, think about comfort first, and then everything else will fall in place. So when I talk about comfort, I'm not talking just about temperature. I'm also talking about visual comfort. You know, if there is direct sun, you're not able to, you will pull down the blinds and the natural ventilation of the open windows gets cut off. If it is too much noise outside, you'll again close the windows. If there is too much smell from outside, again, you close the windows. So all these things, if any of them do not work, then your natural ventilation fails. Similarly, outdoor comfort is also equally important. So if it is so complicated, you might want to ask, why bother? Why bother with natural ventilation at all? Then we'll have to go back and understand why certain places feel much better than others. I guess all of you are architects and you all know that certain places have a much nicer, what we call vibe, than other spaces. And if you go down and understand why that is, for centuries, for many years, anthropologists have always been telling us that, human beings are hardwired to respond to nature. And it's the same response of the relationship in architecture that makes people feel good in certain spaces. So we're all hardwired to be outdoor creatures. We are hardwired to be, in constant touch with nature and the outdoor conditions. And that's when we feel much better. And there are several studies that were conducted across the world, which said that if you have access to natural breezes, natural ventilation, naturally ventilated spaces constantly, if you have good access to daylight and to have good views, then your memory span improves, your productivity improves, even the number of minutes in a day that you sleep also improves. This increases your ability to focus and ability to enhance the cognitive abilities of people. Also reduces stress, because you sleep better, your stress reduces. So these are several studies that were done across in several parts of the world, which said that these kind of having this access really helps in improving. Another very important aspect relevant to what you are doing, net zero energy buildings, is that if you do a fully air conditioned, let's say an academic building in this particular case, because we're looking at two academic buildings. If you do a fully air conditioned academic building, what happens is your EPI is definitely going to be much higher. And with the limited land area that is available, the on-site renewable energy potential is always limited. So the balance of net zero is very difficult to achieve if you go fully air conditioned. If you do partly air conditioned, that is mixed mode, some spaces are air conditioned, some spaces are air conditioned only during summers or the harsh times of the year, and naturally ventilated through the other times of the year, and some spaces are naturally ventilated, then you have a much higher potential to achieve the net zero target. Now, if you do a fully naturally ventilated academic building, you have the potential to go net positive energy as well. However, please remember, you cannot do any of this at the cost of comfort, because then if you do not meet the comfort requirements later on, after you finish design and you're out of the project, the users will usually end up retrofitting the building in the most energy inefficient manner, the cheapest, quickest, most energy inefficient manner, which will completely defeat the purpose of designing a building in a naturally ventilated space, as a naturally ventilated building. So with that, I'd like to sort of quickly go through, what are the various steps and important things that you need to consider in the natural ventilation design of buildings. So let's start with, the different types of natural ventilation. I'm sure you would have gone through this in your learning modules. So there is wind assisted natural ventilation, stack assisted, and night ventilation. Wind assisted is simple. This is something that you see most commonly. Single sided ventilated space, cross ventilation. This is single sided ventilation and wind assisted. Cross ventilation when you have when there is movement across the room. And there's also a simple buoyancy driven stack. This is when warm air rises up, you provide ventilators at the top, and the warm air rises up and escapes through the ventilators. And as it escapes, you're pulling in cooler air into the space from the lower areas. So this is a simple stack driven ventilation, which you see in a lot of older buildings and older houses. Then there is stack assisted ventilation, which is wind assist. This is further stack, that is enhanced stack ventilation. This is when you create things like, you know, yeah, these ventilated cavities, when you create these kind of openings, which means that as the wind flows, it creates a negative pressure on the leeward side, pulling in the warmer air from the rooms. In the process, enhancing the ventilation capability of the space, of these spaces itself. The other way to enhance stack is through solar. You know, you create, you know, you're creating a collector here, which increases the temperature, and then it increases it creates a negative pressure because of the sun or the heat, and then as the breeze, as the air escapes, there's a negative pressure here because of that, and then this sort of pulls in. So this is a solar assisted stack and wind assisted stack, and some simple examples, you know, wind assisted stack could be wind cowls, or even these kind of cowls that you see very commonly nowadays. Simple stack ventilation. Solar assisted stack would be, you know, the solar chimneys that you see, that you are coming across a lot. If you do a bit of internet research and see some of the case studies, you'll see that solar assisted stack is being used quite efficiently in a lot of spaces. And some initial design considerations, very early design stage. So these are just a few thumb rules, I would say, to start off on your design. This is not what your design should be based on, but this could be a start. You know, what should be the depth of the room? If a room is so deep, you know, will if the room is deeper than this, can I actually make it effective in the natural ventilation mode? So these are some small thumb rules that you would have seen in the if you had gone through the CEPT NatVent guide, then you would have seen these kind of images. Is that if it is a single-sided ventilation, you have, you know, the width and the depth to which it is effectively ventilated is twice the height. If you have a kind of a stack that is a ventilator on top and an inlet at the bottom, then it can go up to 2.5 meters. And one more, if you have cross ventilation, though, it can go up to much more. It can go up to 5 times. It can double. The depth of the space can be doubled, and still you can do a good natural ventilation strategy. Couple of other things that you need to be careful about is that you should give equal consideration both to inlet and outlet. Ideally, outlet should be slightly bigger than inlets, if not at least equal to the inlets. And then if you are looking at cross ventilation through several rooms, like you have 2 rooms adjacent to each other and you're expecting the wind flows to flow through those rooms, then make sure that you design the openings between these rooms well. You know, they should be permanent openings. And for stack, in a lot of single houses, in a lot of independent houses, or even in duplex apartments and stuff like that, and in spaces like that, you can use the staircase multi rooms. You can enhance the stack using those kind of spaces. But the most importantly, the amount of ventilation will depend critically on the size and placement of openings in the building. So those little bit on that, and now let's go into a stepwise. What do we design for? How do we go about a natural ventilation design? You know, you go in a stepwise manner. It might look complicated, but it is not. It is, if you look at it from a if you base it on your personal experiences. I'm sure all of you have experienced natural ventilation spaces. If you go back and understand why some spaces work much better than the other spaces, you will start understanding the principles behind those. You'll start understanding why some spaces are better than the others and how you can integrate the same principles. So go back and understand that. Now you go stepwise into different spaces, into natural ventilation design. But before we go stepwise, I know you've been through the climate analysis and comfort, but there are some aspects of climate and comfort I'd like you to give special attention on. Do not consider comfort in natural ventilation spaces to be similar to comfort in air-conditioned spaces. The same design conditions you consider for air-conditioned spaces do not apply for naturally ventilated spaces. You do have to go in for IMAC or NBC. Ideally, IMAC the Indian comfort standards for mixed mode and naturally ventilated spaces, that's the comfort standard that you would have to follow. That will allow you to see that natural ventilation is possible a lot more than you think is possible. But if the moment you take the conditions of an air conditioned space, you limit to your air conditioned comfort limits, then you are losing a lot of potential there. But while you do that, you also understand that comfort is not about temperature and humidity. Comfort especially in natural ventilation spaces and passively designed spaces is a combination of temperature, humidity, airspeed, and radiant temperature as well. So because airspeed has a large impact, you can't also say that overestimate the potential of natural ventilation spaces, saying that you'll increase the fan and keep it at 5. It might not be comfortable for a lot of people. More than 1.5 meters might not be. It might be, you might feel that it is very drafty and not be comfortable. Also leads to a certain amount of noise, background noise, which a lot of people will not like. So do not overestimate. Do be very aware of at what level air velocity is comfortable. And most importantly, passive design and natural ventilation design have to go hand in hand, and all aspects of comfort have to be integrated into design so that your design becomes more successful. So when I mean all aspects of comfort, I mean thermal, visual, auditory, and olfactory. Similarly, external spaces as well. So let's look at kind of you understand, you know what kind of building typology you want to design for, and then split the building based on how you want, what kind of spaces can be conditioned in what way. There might be spaces which need to be fully air conditioned. There might be spaces where mixed mode conditions are applicable, and there would be spaces where natural ventilation is possible. So if you split it up, then you can see what kind of strategies you need to apply for different kinds of spaces. And then coming into climate, what are the aspects? All of you would have seen this before in the webinar on climate, and in your learning modules about climate analysis, about temperature, humidity, understanding how it compares with comfort conditions. But what do you infer out of it that will help you in your design? So let's see what you can infer out of it. So if you put it side by side with with the irradiation, what is the kind of, not irradiation but radiation plots of in the same weather condition, and place it side by side with temperature, humidity, and the temperature difference between night and day. If you have all these things plotted and put together, you will be able to understand that there are times of the year when natural ventilation works very well because the climate is very conducive. It's suitable for natural ventilation because outdoor conditions are very, very suitable. Okay, and that's when both wind assisted ventilation, night ventilation, all of this work. If you go into the monsoon times, if you look at monsoons, then you'll see that cross and stack, only cross ventilation works best, and night ventilation might not work that well because nighttime temperatures are much nighttime temperatures are much higher, and the difference between day and night is not too much. So if you go through all this, you will understand that how to analyze the climate. Then you can zoom in onto the time of the year when you want to, what wind direction you want to work with. You know that natural ventilation can be done effectively during monsoons and winters in this particular case. And then of these two, because they're different wind directions, which one will you actually choose? So because monsoons have higher humidity, this is where only wind assisted stack or wind assisted ventilation works, and solar assisted stack doesn't work. You choose monsoons and you design for monsoons. The reason why we have to go back and look at irradiation is to understand how much shading is required. This again goes back to the thermal comfort and reduction of radiant temperature in your spaces. So this is, you go back and then you strategize what kind of strategies you use for which spaces. So now let's go step by step, and I'll run you through some simulation results and how those simulation results helped in informing design in the design process. Start with these are these always designed for orienting for sun and wind. If there is, if you have the potential to work at a master plan level, where you have the potential to design the blocks, then you ensure that you design to ensure that the wind flow is comfortable, both externally, and every block has a positive and a negative pressure on either sides. This helps you in maximizing the NV potential in those blocks. However, if there is a clash between, orienting for sun and orienting for wind, always orient to minimize solar gains, because the sun is definitely a lot more a harsher element. Then then you go to the next stage of going into the building itself, and you start working on a natural NV network. So how do you do it? I'm going to run through this through a case study. This is a case study of an apartment block, again in Hyderabad, where there were apartments with space with gaps. Every apartment block was had these breezeways in between them, with allowed for ventilation from three sides. So this helped in one way, and then you start integrating, understanding, doing a network diagram. So here you go, there are some spaces where cross was possible. And to be able to do that, you had to open up some of these spaces, like kitchen. If this was a corridor here, see if there is a potential to open up towards the corridor here, open up towards the external utility block. Always try and create cross flow wherever possible. In every room possible, create a cross ventilation wherever possible. Where it is not possible, like in this particular space, the network diagram shows that we are trying to pull the breezes through the door, because there was no other way that you could do it. And in that case, you should be very careful about what kind of door this is, and how you design the door or the space above the door. If the door is kept closed, then this room might not be ventilated at all, and you might completely miss out. So in that case, what kind of room do you want to use that space for, is another decision that you can help make. How do you integrate stack into this whole equation? Try and integrate ventilators, allow for buoyancy driven ventilation by integrating ventilators in all these spaces. This is an example of a building where the orientation is not conducive for sun, but it is conducive for wind, because it was westerly and the winds were westerly. But so what do you do? So then what do you do? You have to go and ensure that your solar gains are minimized and proper shading is provided. So you go around doing a proper shading analysis and understanding what kind of shading is required. So different types of shading devices could be attributed. If you want a full height window, then you need greater shading. If you provide a sill, then you can reduce the shading. You can have a balcony and provide a much smaller screen. Or if you do not want a balcony, you can this kind of shading is also possible. And the client went ahead with this kind of shading where he integrated these things. Now, and then go around and understanding how effective this shading is. When does solar ingress starts? When does it start? Because you can definitely assume moment there is direct sun coming into that space, the blinds will be pulled down if it is still quite warm outside. So in June, there's ingress only from 4:30 p.m. onwards, which is okay. And December, even in December, you should be very, very careful about when the blinds will start being pulled down, because December, as you know, is the time when natural ventilation is the most effective, and it can be used most effectively because external conditions are good. So you do need to look not only in June, but also for a cooler season, because that's when natural ventilation is most used. So, and then check the visual comfort, understand if it is just a balcony, you can see that the amount of direct sun coming in on the daylight levels are very high. If you start providing shading devices, you start modulating it, and the visual comfort and the daylight levels in those rooms are a lot more modulated, makes it a lot more comfortable, which means there's a higher potential for people to keep their windows open with no blinds drawn. And that's the final objective. Then go into the facade materials. Choose your facade materials carefully. This is from a different project. This is based out of Baroda. And there were different types of walls that were being tested. They wanted to go for the lightweight Maivan walls, which are these precast walls, you know, the prefab walls that are being promoted nowadays very commonly. So what happens when you use such kind of walls? Of course, the cooling energy was going quite high. The cooling energy in those kind of walls, when you start providing even a little bit of insulation, the cooling load was, you know, reducing by close to 50% in such spaces. But most importantly, you know, the internal comfort conditions with just the Maivan wall, which is a single 80 mm concrete wall, which has a U value of 3.3 watts per meter square. When you compare it with another wall, even with a small amount of insulation or some form of solar control, some better U value or a much lower U value, meant that in the afternoon, this was a hostel for a university in Baroda. When people started coming in at 6 o'clock in the evening, the Maivan wall had a resultant temperature of close to 35 degrees, whereas all other wall typologies brought it down to 31 or 31.5 degrees. If you had a much better wall material, then it could even be brought down to 30.5 degrees. So the good 4-degree difference between different types of walling systems when people start entering those hostel rooms or hotel rooms. So understanding, or this is what I mean by understanding comfort, understanding thermal comfort from a radiant temperature perspective. Make sure that you do not overlook this, because this means that you will not be able, this means that the amount of heat gain and perceived or felt temperatures in these rooms are going to be so high, whatever amount of natural ventilation you provide would not be sufficient to make you feel comfortable enough. Once you go through those, then come to the window design. You know, it's very important. The fenestration design is probably the most important part after you finish so you know, you provide adequate shading. How do you do it? You can start off with, you know, the information that you get from LECOVIR Design Guide. It's a very good guide. I mean, it's something that you can base it on. However, what you need to be extremely careful about at this point is that understand the difference between the actual window opening size and an effective opening size. You know, what this gives is the free area of the openings, which is not the actual window opening size. It is the effective window opening size. Please be very careful about that. Understand that depending on the opening, depending on the type of shutter you choose, if it's a sliding window, only 50% of the window will be open at any point of time. If it is a casement window, there is a frame component that you need to consider, and only part of that, only about 80-90% of the window can be left open. If it is louvers, if there are louvers integrated into a window, then it means that the opening proportion, the actual effective or free area, is about 60% of the actual window area. So be very careful about how you calculate it, and the details of how you can calculate it is also provided in these guides, both the CEPT guide and the LECOVIR guide. Then in our case, in Indian scenarios or in any tropical country, any NV naturally ventilated space will require you to put in a mosquito screen or an insect screen. Now, you have to consider that in your design, because that has a huge impact on the pressure drop as breezes come in. Even in your in the place that you're staying in, you just notice, if you have a mosquito screen, remove the mosquito screen and you'll immediately feel that you have a lot more breeze coming in. But the moment you put the mosquito screen back, the amount of breeze that comes in reduces dramatically. Now you should consider that in your design, and uh, also be aware of the height of these windows and the density of development. So here is a bit of a little understanding or something that you could use while you are calculating the impact of mosquito screens. What is the kind of mosquito screens, what kind of screens. If it is a bronze wire screen or a metal screen or a SS steel mesh, then the porosity is much higher. If it is fiberglass mesh, the porosity is lower. And if you have different, if it is dusty, then the porosity goes down even more if compared to when it is clean. So do consider this, because this is very much a required element in every naturally ventilated space. And as I said, understand that there is a profile. As you go higher, the wind speeds are greater. So you can take this, you take this, actually it is quite an advantageous little thing that you can use in your design, because as in the lower spaces, you might have to increase your opening sizes, but as you go higher in your building, your opening sizes could actually be reduced. And once you use these thumb rules or these guides to arrive at your opening sizes, then start using your simulations tools to do sensitivity studies and see if they're being as effective, or if they need to be reduced, or if there is an opportunity to reduce, or if you need to increase them. So because you cannot go into simulation without a baseline. You need to do a baseline and then do the simulation, so that otherwise you'll be doing simulation forever. What takes maybe 3-4 hours, if you base it on some kind of a baseline, some kind of a standard or a thumb rule, it would take, maybe when you do simulation, would take half a day to get your result. But if you don't, then you might be doing your simulation for 3-4 days to get to the same result. So following those thumb rules are very, very useful and important, especially at early design stage. Another reason why you do simulation is because you don't have time in the early design stage in practice. You'll have very little time. You'll get time only later on in the design. Now, in this particular case, there are 3 different types. If there is a if you can, as you can see in case 3 versus case 1. Case 1 is where the windows are open only from a single side. There is no cross ventilation, and case 3 is where there is cross ventilation. When you do that, the difference between the two is dramatic, is quite a bit, and you can see that the comfort levels go up quite a bit if you have cross ventilation compared to a single-sided ventilation. Now, coming to a next case, this is about secure windows. We architects love, or a lot of people love to have these large French windows. But how many people are comfortable keeping those French windows open at night? No one likes grills nowadays. No one is designing for grills. So what happens is, when you're sleeping at night, these windows tend to be closed because these are not secure. People don't feel secure about keeping these open. So when that happens, there's a large impact on the comfort, because at night your building is not cooling down and you're completely losing the ability or the advantage of night ventilation. So this is another example of how various cases. So you have a case where it is just a single big window. If you add external shading, the number of comfort hours in this particular bedroom go up from 52% to about 55%. You improve the glazing a little bit, because these are French windows, that improves. And then you reduce the window size, because you design for daylight. You want to optimize on the daylight, on the window size. You don't want a huge window size, because it increases the amount of solar gain. So you do reduce the window size. It has a small negative impact, but the moment you integrate another window for cross flow ventilation And when you integrate and also increase the height of that window to maximize stack, you can see that that's when, you know, your comfort is maximized in these in all these bedrooms. You know, last case is when the height of the window goes all the way up to beam bottom. So that's when the impact of stack is coming into play, and you're able to maximize your comfort because you're able to get rid of that. So this is it's a very, very clear indicator that cross ventilation has a certain impact, but when you combine cross ventilation with stack ventilation, be it buoyancy driven, be it wind stack driven or assisted stack, that's when you maximize. So when you do natural ventilation, always combine wind assisted with stack ventilation to get the best results. Same kind of things. This is specifically in case of the living room, you know, large open, what you have, large French windows. When you have these French windows, like this is the case, you know, you have these large French windows which will end up being closed at night because no one's comfortable keeping them open. Most people are not comfortable keeping them open at night. The moment you provide more secure openings that can be left open at night with some grill or something, so what happens in this particular case is that you're allowing the building to cool down at night. It drastically improves the comfort in these spaces. You know, you're able to increase it from around 47% to around 55%. So that's the kind of impact night ventilation has. So always think about night ventilation. Don't think that if you design a window for the day when people are occupying the space, that would be sufficient. You have to design for times of the year and times of the day and night when people are not around, when it is closed, and then you'll have to, sorry. Yeah, when you have to design for nighttime, you have to design for times when people are not occupying the space, so that what happens otherwise, if someone's going on a holiday and you cannot leave your windows open, the heat build up in the space is so great that it impacts it affects the furniture in the houses sometimes, especially if you're away for a whole summer, for a month or so. Then through the summer the heat buildup is so high. After you come back, it takes time for the building to cool down. So think about those. Think about times, secure openings at night and holidays when the building is not occupied. So think about this background ventilation as well. It's as important as designing ventilation during the daytime. And finally, there are, you know, you can do a lot using simulation tools. You can, there are a lot of things you can do by using thumb rules and standards. However, if you use the right kind of simulation tools, what happens is you will be able to test them out. You know, in the earlier days, this ability was not possible. You know, this wasn't possible. This kind of potential of testing a building before it is built was not possible. So the learning process is very long. You know, you make a mistake on one building, you correct it in the other, that might not be the best case scenario, you correct it in the third. So you're losing, you know, a lot, you're making several mistakes before you get to that level where you are doing it right. Now, the simulations tools can help you speeden that process. You can test various scenarios and come down to and zero in on one or two strategies that will work. You zero in on the type of windows, the opening proportions of those windows, the size of those windows, the kind of shading devices, the kind of the height of these windows. You can do a lot of testing at a simulation stage to ensure that the design strategies that you are integrating actually work. Now, however, to do that, you need to use the right tools. You know, these are some tools where natural ventilation can be tested. There are network models and geometrical models. These are thermal dynamic simulation models which are can be used quite effectively to understand or design for natural ventilation. But tools are one thing, but how you analyze the results that come out of tools is another very large part of it. So what are the most useful parameters for you to analyze? One is resultant temperature. it's probably one of the most important parameters, design parameter that you can use to analyze various aspects of your design. Then airflow through the rooms. How much airflow, ACH or in meters per second? How much airflow is going through the room is another one that you can use to analyze your building. Further assessment could be, how much wind flow through a aperture. Surface temperatures of rooms is surface temperatures is a very important aspect for you to understand the resultant temperatures or the thermal comfort in a space due to radiant temperatures of your external walls or external openings. So that's also a very important parameter that you could work to, you could analyze in your thermal analysis. And what are the various things that you can test out? In mixed mode and night cooling studies, you can look at number of cooling hours, peak cooling hours, annual cooling hours. You can also look at how many hours in a year that you can naturally ventilate, how many hours in a year that you have to air condition. So in a mixed mode space, you'll be able to get that kind of information. But to be able to get that, you need to look at resultant temperature as your primary parameter. Now, while doing all this, and this is the finally, I'm ending with this particular slide, because it is while you learn about how to design for natural ventilation, you should also learn about what makes natural ventilation systems fail. And there are so many things some are very, very intuitive. I mean, some are very straightforward, like dust and noise pollution. That if there's too much dust and noise pollution, you will have to close your windows and you can't do much. Mosquitoes and flies, yes, you have to design for mosquitoes and flies. Spiders and spider webs, I personal experience, this is partly with ventilator design. If you keep your ventilators to open outwards, the frequency of spider webs forming there is a lot higher compared to when you keep your ventilators to open inside. Pigeons, it's a common issue that we face nowadays in a lot of apartments. If your window sills are not designed correctly, you have pigeons settling on them, and that means that you will end up closing your windows because of allergens. Rain, very, very important. You have to ensure there is a certain amount of rain tightness, and there is an ability for you to keep your windows open when there is rain. Otherwise, if there's water coming in, no one wants to go about cleaning it. Accessibility of openings. All of us talk about keeping ventilators, using ventilators. All of us say that keep your ventilators open, design or integrate a ventilator. But if this ventilator is not accessible, if you can't open and close them easily enough, it'll always be kept closed. So you're losing the potential for stack ventilation. So in that case, maybe you might lose a little bit on the stack efficiency, but creating one large window from going all the way to beam bottom might be a lot more efficient strategy and a lot more practical strategy than to have two different windows, one lower level and one ventilator level. And then of course privacy and security, and if there is issues of privacy, if people can look in, then you will not keep it open. So do think about all these things while you are designing your windows. If any one of these can mess up with your design. And last but not the least, and especially in academic buildings and office buildings, the code requirements for fire sometimes and a lot of times go against the natural ventilation requirements. So that's again that's an extra complication which you would have to take care of. So with this, I'd like to end my webinar, and any questions you have, I'm happy to answer.
Yes, thank you, ma'am, for explaining the process of designing for natural ventilation and sharing these insights from some really great case studies. And we'll take a few questions now. So the first question that we have is, so we adopt night flush ventilation strategy when there is a substantial difference in day and night temperatures. What is the most we can do if the temperatures do not vary much, like for example, a naturally cold environment?
Night flush ventilation is something that we integrate into a building where it actually goes hand in hand. You might have, you probably would have some, when you were doing passive design, that would have come up. It goes hand in hand with thermal mass. The whole point of night ventilation is that during the day, if you have high thermal mass, then your the building absorbs the heat, and at night you need to design your ventilation so that that heat can be dissipated at night when it is cooler. So that's the principle of night ventilation. Now, in a naturally cold environment, even in naturally cold environments, if the radiation levels are very high, especially during summers, this can be used a lot more effectively actually in cold environments. So what will happen is there is you have the solar radiation. The building starts picking up heat, both external heat from sun and the internal heat because of all the internal activities in the rooms within the building. So it picks up this heat, and at night, even if it is cooler at night, it is a lot more efficient. You need much smaller openings to be able to get rid of that heat. So it can be used in naturally cold environments also if the daytime radiation levels are very high. However, if it is a humid climate where the difference between day and night is not too much, then you can use it effectively in fully naturally ventilated spaces, because you don't want to, there is at least a small amount of potential there. But in a mixed mode space, it might not be as useful.
Thank you, ma'am. Next question. Which type of natural ventilation should be preferred when we have high occupancy and in areas having high humidity? For example, an IT company in Vizag or Kolkata.
Okay. So in that space, in such spaces, what you need to understand is, not the whole building might not need to be air conditioned. You can split it up. You can understand, you can see which spaces can be naturally ventilated and which spaces need to be air conditioned. So there'll be, let's say the office areas might have to be air conditioned because people sit there a lot. Lobbies, entrance lobbies, food courts, these kind of spaces could be naturally ventilated. And there might be some spaces in even these lobbies, let's say let's say guest rooms, or some kind of in between, those lounge spaces, or lounge spaces, or there will be some spaces where you want mixed mode strategies, where you say, okay, I'm going to naturally ventilate it when the weather's good, and otherwise I'm going to keep it closed and have air conditioning. So you'll have to understand, go space by space, understand which space, what strategy can be used. Some spaces fully air conditioned, some spaces could be mixed mode, which means they would be conditioned during the harsher times of the year and naturally ventilated when the weather is milder, and there'll be spaces where naturally ventilation can be done throughout the year. These could be the transitional areas, the food courts, etc. So depends. You'll have to strategize it accordingly.
Thank you, ma'am. Next, can you please specify the standards for absolute naturally ventilated and mixed mode ventilated residential buildings? I think by absolute, the person means totally naturally ventilated buildings, not air conditioned at all.
I think the LECOVIR guide is a great place to start for this. It's exactly this. So I think you should follow the LECOVIR guide for this.
Yeah. Next question. How do we calculate the number of hours when natural ventilation will be effective?
So this you'd have to do through a dynamic thermal simulation. Use IES or TAS or any of these various simulation models that I showed at the end of the presentation. So you'll have to use that to be able to calculate this.
Right. Next question. How do we design windows to keep pigeons out?
Good question. So first of all, understand that, pigeons usually end up in spaces which are overshaded. You know, if there is direct sun on any sill or any part of the window, be it chaja or sill or anything, then you will usually not see too many pigeons. Pigeons come where it is well shaded, you know, and that's when they find it comfortable. So number one, avoid overshading. Okay, optimize your shading devices. Number two, the window sills could be designed with a slope, you know, quite a steep slope, because even a slight shallow slope, I believe, is not good enough to keep them away. But quite a steep slope, if you can keep the external sill at a slope, chamfer it, then that's another strategy to keep pigeons away.
Thank you, ma'am. Next question. Imagine a building like a product where you do not have control on orientation. Please suggest shading mechanism for windows in that case.
So you go, you know, the case study that I showed of the apartment building. If you come to South India, especially Hyderabad and I think maybe even Tamil Nadu, you will notice that Vastu plays a very major role, and you'll end up seeing that all buildings, almost 90% of the buildings, will be facing east-west. You know, you will not find north-south facing buildings. So you will always, especially residences, you'll always find this problem. So it has to be case by case. What is it that they're comfortable with? So always provide various options for shading. Look at the shading angles. Again, the guides that you have done before about calculating shading angles, your learning guides all explain how to do that. So follow those guides and understand what kind of shading angles are required for which orientations, and look at various shading strategies and understand and try and make them, as much as possible, try to make them static.
Right. Thank you. Next question. If we are using induced ventilation, is there any cutoff speed of wind to induce a negative pressure?
When the wind speeds become too high, then it'll start becoming uncomfortable. I don't know, actually. I'm not very clear of this question, actually. I'm not able to understand what you mean by cutoff speed of wind to induce negative pressure. I don't quite get it. The higher the wind speed, you'll usually have a greater negative pressure. So,
yeah, I mean, so this question was asked by Aditya Anand. So, I mean, can you please ask the question with a little more clearer language, and I can take it up again in some time. We can move forward to the next question. The next question is, so if the air is polluted, like in New Delhi, then how should we take in natural ventilation? Are there any mitigation steps?
this is very difficult, actually. If the air is polluted, natural ventilation is very, very difficult. There are some studies which say that vegetation helps with PM10. It doesn't help that much with PM 2.5, and it doesn't help too much with the SOx and NOx emissions. So vegetation helps. Green screens, vegetated screens, these help a little bit, but not completely. So it's very difficult. You might have to come up with strategies of mechanical ventilation, using fresh air. You might have to come up with alternative strategies. It's very difficult to get rid of pollution, especially the levels of pollution you see in Delhi. However, that doesn't mean natural ventilation will not work in Delhi. You understand that the pollution happens for about 3 months. So rest of the year, January, February, maybe February, March, sometimes of the year are okay. So it doesn't mean that you don't design for it. But most importantly, you're designing buildings for 50 years, 50 to 100 years. Pollution is an issue that is there right now. Okay. Now, hopefully, people figure out, the government, our authorities will figure out of how to overcome this, and hopefully maybe in the next 10 years this wouldn't be a problem, and hopefully it shouldn't be a problem. In that case, you're designing for today, and 10 years down the line, you're not going to no one's going to retrofit the facade. to integrate natural ventilation. So designing for natural ventilation is good. You might not use it today, but it's a great future proofing strategy, even in locations like that.
Yeah. Thank you. Next question. How do we come up with the size of inlet and outlet sizes for windows depending on wind speed? Are there any thumb rules or guide which we could follow?
So there is LECOVIR guide, which gives you, and there's also CEPT guide, 6CM10. It also provides you a calculation methodology of doing this.
Thank you, ma'am. Next question. You have mentioned that there could be cases where an attempt to integrate natural ventilation could violate safety norms in a building. Could you give an example of such a scenario so that we can try and avoid it from happening?
Okay. Fire safety norms. So sometimes in spaces like lobbies, in a lot of buildings, we would want lobbies to be naturally ventilated, and lobbies also have staircases. So what happens is because you'll have to do a very compact design, you would want to open up the lobbies. You might have to keep the staircase on the external side and want to open up the lobbies to the outside environment, or create the windows through the staircases, the staircase well. Maybe even use the staircase well as a to enhance stack ventilation in such spaces. You might want to do that. However, the fire code requires you to seal the staircases, and you will not be allowed to open up any internal spaces into your staircase well. So that's one of the areas where your strategy goes against the fire norms. There are also norms about having fire rated doors in long corridors, in some corridors, depending on the type of buildings it is. So these are some of the things that you would have to take care of and come up with alternative strategies.
Right. Thank you, ma'am. Next question. In the Aga Khan school in Hyderabad, when the humidity levels inside the classrooms were higher, what strategies were used for dehumidification?
Okay. The humidity levels were higher not because the humidity levels were higher outside. The humidity levels were higher because ventilation was not effective. So first of all, improve ventilation, and that took care of the humidity levels. Second thing, yes, there were times of the year when humidity was higher. It went up, but why do we get scared of humidity? What do you do usually when there is higher humidity? You don't go about using dehumidifiers everywhere. You just turn on the fan. It improves your comfort quite substantially. So that's what we do.
Thank you, ma'am. Also, we got another request in our chat window. So can you please go to the software slides where you spoke about the different softwares we could use? And probably the participants can take notes here. Yeah, so these are the, yes, ma'am.
Yeah, there are probably others. There are actually other ones as well, but these are some that are most commonly used.
Right. So those were the questions we had for today. And with that, thank you so much, Swati ma'am. The question and answers was very helpful too. And I hope that our participants can make the best use of the knowledge and practices shared with us today. Also, I would like to thank the Department of Science and Technology and the Ministry of New and Renewable Energy and all our sponsors and affiliates for their support. Thank you everyone for participating today, and we will see you next week. Thank you, ma'am, once again.
Thank you, Yashima. Thank you, Prasad. And all the best to all of you. And I hope this is an exciting, I'm sure this is a very exciting competition, and I wish you all the luck. Bye, everyone.